Welcome back. Today we are going to do the last topic of the compact microstrip antenna design, that is broadband and compact MSA. As we have seen in the earlier lectures, there is a problem with respect to the compact antenna. Rather, the demerits are the lower bandwidth, the perturb or disturb radiation pattern, and the reduced gain. By employing different techniques of wideband configurations, here we are going to increase the bandwidth of the MSA. In some cases, even the gain will be enhanced. Okay, so these are few techniques which we are going to study in detail, how the techniques are applied to increase the bandwidth in compact designs. So first is suspended, shorted and slot cut MSA. Suspended configuration, as we know, it increases the substrate thickness, and the substrate thickness is directly governs the bandwidth of the antenna. So that increases the bandwidth even in the compact designs. So that suspended configuration we are going to employ to increase the bandwidth in compact design. Next is the different feeding techniques. Remember, when you increase the substrate thickness, as we have learned in the wideband antennas, that when you increase the substrate thickness, the probe inductance limits the antenna bandwidth. So there, modified feeding technique configurations can be employed that increases the antenna bandwidth for a thicker substrate using a compact design. So use of modified feeding techniques will come to the rescue to increase the bandwidth in compact MSA. That is second the technique. Third technique is the multi-resonator configurations in the form of gap coupled and stack configurations. We have seen it in the wideband technique using the gap coupled and the stack configuration that additional patches are used either in the planar layer or the stack layer. So there these configurations will be used to increase the bandwidth of the compact design. Of course, slightly it increases the patch size, but definitely it is much smaller as compared to the area of the conventional MSA. Also, looking at the compact design, appropriate selection of the parasitic patches can be done that effectively does not increase the patch area. So that those kind of configurations also we will talk. Further, we will consider these widely used resonant slot cut techniques which maintains the single patch configuration present in this compact design, but by embedding the slot, it increases the bandwidth. In fact, there are many techniques. I have just listed few of those techniques to increase the MSA bandwidth, but actually speaking, there are many such techniques which are available. Okay, so now the first technique of the compact design is the suspended, shorted and slot cut MSA. Shorted or slot cut MSA on a thicker, lower dielectric constant substrate is used. As we know, it is the simplest method to increase the antenna bandwidth, and generally for a substrate thickness more than 0.40 lambda naught. Okay, now lambda naught, it can be lambda g if you are using a suspended dielectric substrate. So here, if you are using more than that much substrate thickness, then the probe inductance limits the antenna bandwidth. Okay, so here this particular configuration is generally used for a substrates which are limited in their thickness till 0.04 lambda naught. Further, here use of electromagnetic coupling from the feed to the shorted patches or the slot cut patches increases the bandwidth in these designs. Modified feeding techniques like L-probe and folded feed or even proximity feed can be used to increase the MSA bandwidth in these suspended designs. Remember, suspended we are going to use it everywhere. We are going to use it in gap coupled design, we are going to use it in slot cut design, we are going to use it as well as it is in a modified patch shape design. So this is in general we are going to use, but in general we can call this as one of the technique to increase the bandwidth. Okay. Here, what I mean by this, here if you see the configuration, this is one such design what we are talking. Here you have a shorted patch. So this edge of the patch is shorted. It is shorted to the ground plane, and then you are using a pretty thicker substrate edge. A thicker substrate is used, that is edge, and then naturally when you use a thicker substrate, it will add to the probe inductance. But by using a modified feeding technique like a L probe feed, you are reducing the probe inductance. What it does, it provides an electromagnetic coupling. It provides an electromagnetic coupling between the L probe section, the horizontal section of the L probe, and the shorted patch, and that gap coupling increases the bandwidth, plus this capacitance which is formed between a L probe and a patch that negates the inductance of the feeding probe. So this capacitor negates the inductance, and together it increases the antenna bandwidth by reducing or doing some kind of a probe compensation. This probe compensation is something very important for a thicker substrate design. Okay, so what we have done, we have a compact antenna, we have a shorter antenna, we are using the thicker substrate so that the bandwidth is increased. To limit or to compensate for the longer probe, you have used this modified feeding technique. Now since the thicker substrate is used, your antenna efficiency, radiation efficiency is also increased. It increases the antenna gain. So it increases the gain as well as the antenna efficiency and hence the bandwidth. Okay, so this is one such technique of electromagnetic coupling. Remember, the design guidelines and everything are quite available in the literature. One such thought process of designing this configuration, I can approximate this as a section of folded monopole antenna. And by considering this as a section of folded monopole antenna, which is gap coupled with the shorted patch, okay, this is actually a shorted patch, I can design the configuration for the given frequency. So there are design guidelines which are available in the literature, but the general concept goes like this. In fact, the reference paper for this configuration I have provided here, okay, which I have taken from. Similar in fact, there are many things which are available now. Modified feeding techniques. Here you can use a L probe, you can use a suspended inverted feeds, you can use a T-shaped probe feed, you can use a proximity feed. Ultimately, what you are doing, you are limiting the substrate thickness of the inductance or the probe feed, and then you are using some modifications to feed the antenna. Now, in this configuration, just look at the in both the other configurations. Look what we have done. Here, a shorted patch is used. Okay, since the thicker substrate is used. Remember, thicker means how much thicker? In terms of lambda, one has to judge what is h by lambda. So generally, thicker means more than 0.07 lambda or more than 0.08 lambda. We call them as a thicker substrate. So here, what we have done, this is a thicker substrate which is used. Then you have a L probe section. Ideally speaking, your probe will go till this height. Okay, the probe will go till this height to feed the antenna, but that will increase your probe inductance. So what we have done, we have actually created an inverted L section of this probe. Okay, and then at a lower height, we have feed this probe. So that creates a thinner value of the probe inductance, but still you are effectively feeding the antenna at a thicker substrate because this vertical section is directly connected to the patch. So using this modified L probe feeding kind of a technique, in fact the other configuration also is similar line, you can increase the antenna bandwidth by compensating the probe inductance. So in this case, what we have done, we have used a thicker substrate, we have used a modified feed, and then we are increasing the bandwidth by using these two combinations. Okay, you can use the air substrate also here. You can actually fabricate this antenna on a suspended microwave substrate also and design the configuration. N number of possibilities are there, but generally in this kind of configuration, air substrate provides that design flexibility and simplicity. Hence we use air substrate design for this configuration. Okay. Again, the reference paper for this is available. Remember, I am discussing few of the configurations. There are n number of configurations which are possible. I am just taking out few configurations which can be classified into different methods what we have discussed about. So there are actually n number of configurations reported in the literature by different researchers. I am just discussing few of them here. In fact, you can also come up with different configurations by modifying a given patch geometry. Okay. So next technique is a multi-resonator configuration. Multi-resonator we are using gap coupled and stack designs. Okay, you can use a gap coupled and stack designs of the compact patches put together and appropriately placing them such that overall size does not increase. So using these configurations we increase the gain, and here radiation pattern thus shows a high cross polar using a reduced gain because we are using a slot cut patch. We will directly go to the configurations, there only we will understand what exactly we are doing. Okay, so here what we have done, we have a circular microstrip antenna. By using the symmetry of the circular microstrip antenna, we create an individual semicircular patch. which has the same resonant frequency as that of a circular patch. Now what we do, we actually gap couple two such semicircular patches. When we gap couple two such semicircular patches, two resonances are created inside a structure, so the bandwidth increases. Area remains the same, it is the area of a circular patch, but two resonances are there that has added to the impedance bandwidth of the configuration. So this is one such configuration. In fact, same thing you can apply it to a gap coupled half ET MSA, because half ET MSA is a compact configuration of equilateral triangular microstrip antenna. So similar technique I can use. Similar technique I can use in rectangular patch also, but there slight variation in the frequency will happen because patch width is being reduced. This is what I mean by a configuration. Here I have used a two gap coupled half ETMSA configuration. Remember, the total patch area remains the same. The total patch area remains the same, so I am not increasing, I am not losing the compactness of the overall structure, but I am increasing the bandwidth because I am adding additional resonator. Remember, for increasing the bandwidth, main concept is putting additional resonator in the structure. Okay, so this is one such configuration where you can increase. In fact, this is more interesting design. Okay, here just look at what I have done. I have used both the compact techniques to realize first the compact configuration. Look at this patch first. This is your C-shape antenna. So it is a C-shape antenna, it is a slot cut variation of the rectangular patch. It will give me a compact design for a given frequency. It will reduce the patch size. Now inside this C-shape area, because that is an empty area, I can utilize that empty area to put another gap coupled patch which is also a compact design. So here I have used a shorted configuration which fits inside the empty area. Okay, why shorted configuration? Because I can appropriately tune that shorting width ratio so that the frequency of this patch can be tuned to the frequency of this patch. And remember here, this patch is a quarter wavelength resonator. Why? It is a shorted design, whereas this patch is a half wavelength resonator. So by appropriately selecting the patch dimension, by appropriately selecting this shorting ratio, and by fitting that inside the C-shaped slot area, the gap coupled configuration is realized that enhances the bandwidth. Now here you will see another modification is done. This is a hybrid mode of coupling. Now in some configurations, depending upon their field distribution, because see, the gap coupling is a function of field distribution which is present across the patch periphery. So depending upon the field distribution which is present, sometime I need to enhance the gap coupling. So for that, I put this additional coupling strip. I put that additional coupling strip at a point where the field is maximum for the two patches. Remember, here the field is maximum for the shorted patch, but the field is minimum here. Here the field is maximum for the C-shaped patch, but here the field is approaching null. So in between, I put a coupling strip. It is like putting an additional strip so that the coupling between the two patches is enhanced further. Remember, it's not a direct copper contact what we are doing, but it is a strip which is placed, which is a non-metallic, rather the bottom portion of that strip is non-metallic one, and there is no direct soldering of the two patches what is done. So here by putting this additional covering strip, you can increase the bandwidth. This is called as the hybrid mode of coupling. In some cases, in some configurations, you may see these designs where a direct shorting is also done, but there the fundamental mode of the patch changes. This mode remains the same, but the fundamental mode of the patch changes. And while putting a shorting post, one has to be very careful. Modes of the patch are not getting disturbed when you are actually soldering it. This is not actual soldering. Here you are just putting an additional strip which is enhancing the gap, or it is enhancing the electromagnetic coupling. So this is called as the hybrid mode of coupling, and this is one of such super compact configuration. One more configuration will come now where similar configuration, similar technique is employed. Okay. This is what I mean by. Here you have a ring antenna. Okay. Here you have a ring antenna. So I am using a slot cut technique. So I have created a ring patch. I have reduced its frequency. So I have an empty area inside the ring patch. So I can utilize that empty area by using a shorted gap coupled patch. So I have put a shorted antenna inside this ring area, and the gap coupling between them increases the bandwidth. Now to tune two frequencies, what I will do, I will keep this ring frequency constant, I will not disturb it. But I will change the shorting width ratio onto the shorted gap coupled patch, and then I can tune its frequency with respect to this so that a broadband response is obtained, because the tuning of frequencies is required so that the appropriate placement of the two frequencies is achieved, and then you get a wider bandwidth. So here in this case I have not increased, or in the previous configuration I have not increased the total patch area. I am using the empty space which is present inside that compact antenna to put additional patches and increase the bandwidth. Okay, and then overall bandwidth is increased. In fact, this configuration helps to increase the gain also, because slight increment in the aperture area is also achieved. Of course, not in the line of 3 dB increment or like that, but it does give me some increment in the antenna gain. But these are some novel techniques which are there. In fact, one can look at similar such configurations where you can effectively utilize the patch area or the empty space around the patch area and increase the bandwidth. Okay, now the most important one, resonant slot cut designs. In the wideband antenna, gap coupled techniques is heavily used, and since 1995, this resonant slot cut design technique is heavily used. Here, the same technique I am employing for a wideband antenna in the shorted design. What is done, I will not get into the details of what exactly slot does. That we will cover it in the wideband antenna chapter. But here I will just introduce what exactly is being done to increase the bandwidth. So you have a shorted patch. You can have either a complete shorting width or a shorting post depending upon your desired frequency. Okay, because as we know, a shorting width will have a certain frequency. Further reduction in that frequency or the maximum reduction will be obtained if I just put a single shorting post. So here I have just put a single shorting post, so maximum reduction in the frequency is possible, or the maximum reduction in patch size for a given frequency is possible. Now in that I have cut a slot. So a slot, it is said that it introduces an additional resonant mode in the structure, and then that resonant mode along with the fundamental shorted patch mode increases the bandwidth. Over the last few years, it is found that in fact slot is modifying the resonance frequency of the higher order mode of the patch, which is maybe a 3 lambda by 4 mode or another modes, and that with the fundamental mode is increasing the bandwidth. So those information is available in the literature, you can refer that. Otherwise, the simple understanding is slot is redistributing the resonant modes of the patch depending upon the slot position and the feed position, and with the fundamental mode it is increasing the bandwidth. So this is the wider band response what you have obtained. Similar concept, in fact this configuration came first and then this, because you can see this is the half U slot configuration, this is the compact variation of this. So in this case also, against the U slot, against the half U slot, I have used a full U slot. The concept remains the same. A resonant slot or a slot is introducing or redistributing the resonant modes of the shorted patch itself, and along with the fundamental mode of the shorted patch, it is increasing the bandwidth. Okay, here neither I have used modified feeding, coaxial probe is used. You can see that here as well as here I have put a coaxial probe. Okay, and then I am not using any modified feeding technique, so that complexity of designing a modified feed is removed, and simple resonant slot gives me a wideband response. In fact, in my opinion, this is the best configuration to realize compact as well as wideband response. You can look into this. There are many such configurations which are available in the literature. It is very difficult to cover in this mode of lecture, but there are n number of configurations. Do refer literature which is available, and then you will see many different such configurations. Okay. So in fact, the reference paper for this already given over here. Okay. These are just another variations. In earlier cases, we have used a single shorting post. I can do a similar complete shorting and I can realize similar configuration. The concept remains the same. This is one of the best configuration to realize a compact as well as wideband microstrip antenna. Okay. Remember, this technique cannot be directly used, and the role of a slot here is not to realize a compact configuration. Here I am not mixing two compact techniques. Here I am using this wideband technique, because see, that slot position is not going to reduce the frequency. It has a role in perturbing the higher order mode and redistributing the resonant modes of the shorted patch to give me a wider bandwidth. So that distinction should be very clear from from the reader's point of view, that this slot is increasing the bandwidth because it is affecting the higher order resonant modes, whereas other slots which you have seen in the H-shaped shorted design, which I have discussed earlier in the last lecture, that is reducing the frequency. That is reducing the fundamental mode of the freq patch, but this is affecting the higher order modes of the patch. That is the difference which is present over here. The reference for this paper is also shown. In fact, there are many such variations. I can design the wideband antenna using a E-shaped patches also, V-shaped slot also. There are n number of configurations which are possible to realize. That's what I mean by this. This is the E-shaped patch. So you have a E-shaped antenna. I can use the symmetry of that, something very similar to what we have done in circular and equilateral triangular. And I can have a single slot cut antenna, which is a single configuration, which is reducing 50% patch size against the normal E-shaped design. Okay, so this also I can, in fact there is a similar design available in the literature, that I can use in case of U slot design, I will just have a symmetry with respect to the center line. I will realize a half U slot cut non-shorted antenna, where antenna operates at the same frequency, nearly the same frequency, but gives me 50% size reduction. Very similar on these lines. So here we complete all of your compact and wideband configurations. In these lectures, we have studied the basics of compact MSA, different techniques to realize the compact MSA, the merits and the demerits of every technique, and then we have talked about how the bandwidth can be enhanced. Remember, modifying the radiation pattern is a pretty tricky job in case of compact shorted antennas. Why? Because with the shorting post, the field distribution is perturbed itself. So by incorporating those gap coupled configurations where C-shape and a slot shorted patch, or a ring shape and a shorted patch, I may slightly get a better radiation pattern on the similar line of a slot cut patch. But in these shorted designs, the radiation pattern does remain conical. It does offers me a higher cross polarization level. So here my main thrust was on increasing the bandwidth of the antenna rather than realigning the radiation pattern. That realigning of the radiation pattern can be possible by using a gap coupled configurations of the slot cut patch only, where C-shaped patch is gap coupled with C-shaped patch, or a C-shaped patch is stacked with C-shaped patch, or other H-shape or bow tie variations. So modification in the radiation pattern is possible if I use only a slot cut patch, but bandwidth enhancement is possible by using a shorted as well as slot cut antenna, but those slot cut antennas are slightly different in their function. So in nutshell, we have completed your compact designs, how the compact antennas are done, a comparison between various compact shape, and then few of the papers we have referred from the reported literature. There we have discussed the different configurations, different techniques to increase the bandwidth. 4 such techniques we talk about. In all these techniques, main thrust is to use a suspended substrate or a thicker substrate and use modified feeding techniques. Just one more point here. Why we have not used a modified feeding technique? Here, a slot provides a probe inductance compensation. Now, how exactly does that? Because slot effectively changes the patch width as seen by the coaxial probe. So, when you change the patch width, definitely the capacitance of the effective patch changes, and that gives me a probe inductance compensation. So, it is reported in the literature that slot cut antenna, there is no need to use a modified feed, even if on a substrate thickness of 0.07 or 0.08 lambda G, you can obtain a better impedance match because slot only provides that without using any modified feeding techniques. So here we complete your compact antenna chapter. We have covered all with a variety of compact techniques. We have covered different 3-4 configurations, 3-4 techniques to realize the bandwidth increment, and most prominent of the all is definitely a slot cut technique. So here we complete your compact microstrip antenna design topic. Thank you.